Now to tonight's program. Priyamvada Natarajan is a theoretical astrophysicist who researches gravitational lensing and black holes. She is a professor in the Department of Astronomy and Physics at Yale and the Niels Bohr Institute at the University of Copenhagen, Denmark. A recipient of fellowships from the Guggenheim, Radcliffe, and Rockefeller Foundations, among others, Natarajan currently serves on the advisory board of NOVA Science Now and as a fellow of the American Physical Society, the Royal Astronomical Society, and the Explorers Club. She joins us tonight to discuss her new book, Mapping the Heavens, the radical scientific ideas that reveal the cosmos. Please join me in giving a warm town hall welcome to Priyamvada Natarajan.
So first, I want to say what a pleasure, delight, honor, and privilege it is to have the opportunity to speak to you all and talk to you about my book, as well as what really made me fall in love with science, to the exception of almost everything else, actually. So my family is constantly complaining about how I'm such a workaholic because it doesn't feel like work to me. So what I wanted to do was to actually read a little bit from the preface of my book to give you a sort of an idea of my motivations for writing the book. And I just wanted to impress upon you that one of the key motivations for me was to sort of demystify, not just share the discoveries at the cutting edge and make them accessible in terms of the work that's gone into it and how our understanding of some complicated phenomena like dark matter or black holes is changing, but also to elucidate the process of science, because I think to demystify the process of science, because I believe very strongly that the current rampant disbelief in science stems from the fact that the contingent nature, the provisionality of science is something that's very hard for the public at large to understand. And I think cosmology has a very particular role, and I think an important role to play in terms of getting fans towards science. And that is because, unlike many other fields in science, the night sky belongs to all of us. We just have to look up, and it's there, and the glory and the awe of the night sky, right? And from time immemorial, human beings have been able to not fathom it, to be overwhelmed by it, and moving on to, as I'll talk a little bit later about, trying to comprehend the universe, and not necessarily in the beginning, early on, trying to find explanations for phenomena, but then eventually with science, we have sort of reached a stage where we're trying to find and have been finding explanations. And that we're actually in a particularly special time at the moment, the last 20 years or so. And a lot of people have said, my colleagues call it the sort of golden age of cosmology. And there's actually a really good reason for why it's a golden age, because I think that after a long time, the maturity of our theoretical understanding, the sophistication of our instruments and tools that allow us to get the data, spacecraft, detectors, and the advanced computing, they're all aligned at the moment. So we can actually make the best. It used to be in the 1930s to 1950s, because our instruments, we hadn't discovered and invented a lot of the instrumentation. You could have a whole bunch of theoretical ideas that may not be testable all that soon. And I think what is exciting about being a scientist for me personally is that, for example, one of the problems I work on is black holes. I won't be talking about black holes today, I'll be talking about dark matter. It was a toss-up, which one to pick. Is that, with some of my research group, we proposed a new model for how you could form the first black holes. And these are conventionally one believes that the black holes form from the end states of stars. Stars sort of exhaust all their fuel, they explode, they leave behind a little black hole. So it turns out that we see supermassive black holes in the universe, and therefore it would be convenient if there was some other way to make black holes very massive from the get-go. So we figured out that the physics allows you to make very, very massive black holes bypassing the formation of a star. And these are called direct collapse black holes. And what is very exciting to me is that the upcoming James Webb Space Telescope, which is going to be launched, everything going well, in a couple of years, one of the key science goals of that experiment, of instruments on the James Webb, is to find the most distant, therefore the first black holes. And we believe many of the early black holes were probably direct collapse black holes. So, within my lifetime, within the last 15 years, this is an idea where we wrote the first paper in 2006. So within 20 years, this idea stands to be validated, confirmed, or, shown to be wrong. Obviously, I'm hoping it would be lovely if it was right, but it's okay. I mean, I think the fact that, you can come up with an idea as a scientist, for me, that's the privilege. And I feel that it's been remarkable to be born now, where you can come up with an idea and within 20 years it'll be tested. Before my lifetime, in my lifetime, the idea could be tested already. So the pace of science and technology is just incredible. So I wanted to read a few bits and pieces because I think that they sort of might give you a better idea of where I'm coming from. And because I can tell you that, I'm very interested not only in obviously doing the science, but also in the history of ideas. And I sort of have an academic interest in it as well as an sort of intellectual curiosity about it. And that's what sort of got me to think about writing this book. And I think so let me read a few bits and pieces that are. So our map of the cosmos has altered dramatically in the past 100 years. In 1914, our own galaxy, the Milky Way, constituted the entire universe, alone, stagnant, and small. Cosmological research has relied fundamentally on classical conceptions of gravity in the 17th century. Modern physics and the triumphs of general relativity have shifted humanity's entire comprehension of space and time. Now we see the universe as a dynamic place, expanding at an accelerating rate, whose principal mysterious constituents, dark matter and dark energy, are unseen. The remainder, all the elements of the periodic table, the matter that constitutes the stars and us, contributes a mere 4% of the total inventory of the universe. We have confirmed the existence of planets orbiting other stars. We question the existence of other potential universes. This is remarkable scientific progress. Cosmology, perhaps more essentially than any other scientific discipline, has transformed not only our conception of the universe, but also our place in it. This need to locate ourselves and explain natural phenomena seems primordial. So, there have been ancient creation myths across cultures, and it's remarkable to see the similarities in the mythology that the ancients had. And we need to sort of remind ourselves that myths were their way of making sense of the world, right? They, in the absence of reasoned understanding of laws and principles and that explained the order and the patterns, they came up with myths, and they came up with these unseen forces because they really didn't comprehend what was going on. So there are many books that tell the history of cosmological discoveries, but my goal here is to recount how scientific ideas have been developed, tested, debated, and eventually accepted. In particular, I trace the development of radical scientific ideas that have continually reshaped our cosmic map. I find the process by which these ideas have gained traction and advanced from obscurity to acceptance deeply fascinating. In cosmology, the making and remaking of maps often reflects this process, leaving behind cartographic evidence. And so in the book, I actually use maps as literal maps, as well as metaphorical maps, and when I refer to worldview as a map. The acceptance of new ideas is not linear, is not instantaneous, and it's always contested. As scientists have challenged prevailing understandings of the universe, our worldview and metaphorical map have morphed ceaselessly, requiring us to adapt and to be open to change. This is a story of extraordinary leaps of imagination, of radical new ideas fueled by discoveries and data. The journey to acceptance of an idea reveals many other facets of science. And these are the facets that interest me greatly. The emotional, the psychological, personal, and social dimensions that extend beyond the purely intellectual pursuit of knowledge. This view is contrary to the popular perception of unbiased inquiry by purely objective researchers engaged in deriving some fixed truths from nature. The fact is, science is ultimately a human endeavor, therefore it's laced with subjectivity. Controversies and disagreements within the scientific community are an integral part of the pursuit. And these debates are illuminating precisely because they show us in high relief how new ideas struggle to finally garner acceptance. So in the book, I really talk about some of the radical scientific ideas in cosmology in the last 100 years and focus in particular on the process, the genesis of the idea, the process of acceptance, the pushback, and this is all from within the community of scientists, and how eventually the idea got accepted. So anyway, so that is sort of my take in terms of the particular angles. And I'm also interested in the sort of interplay of ideas and instruments that has generated all this progress in the last 100 years or so. And I'm also interested in how the doing of science has changed over the last 100 years. So, now science, it's big science, very large collaborations in most scientific disciplines. So this trope of this lonely scientist with unkempt hair sort of, figuring it out on pencil and paper, that's not quite, that doesn't capture science as an activity anymore. But there is a danger that all of science is going to become big collaborations and it's going to be safe science by consensus. You have teams, and these teams have to get funded because it costs a lot of money to answer the questions that we have in front of us now. So I also strongly believe, and I advocate mildly in the book, that we should allow many different kinds of styles of doing science. So I, for one, have not joined any of these large collaborations because I feel that by working in small groups, you can take very different kinds of creative risks that you cannot take if you're in a group of 1,000 or several hundred. But anyway, I will, let me just get on with talking today a little bit. I'll focus on the idea of dark matter and why was the idea of dark matter proposed? And it's an interesting idea. It did not come out of a theoretical, abstract mathematical calculation. The idea came out of an empirical need to explain an observation. And if you think about, so in a way, when I think about the two big ideas that I work on, one is dark matter, which was completely empirically, the origin was data. It came out of observations, as I will share with you. And the other idea of black holes, so black holes were actually proposed as a mathematical entity. They're a mathematical solution to Einstein's equations, right? And then they eventually became real, that there were actual real astrophysical objects that corresponded to and that had the properties that we ascribe to this mathematical solution, and that they exist in nature came afterward. So things are just the other way around for black holes. And that's really fascinated me. And of course, I've always been deeply drawn to sort of the unseen, the thing that you just can't quite reach. And I think that was probably what, if I think about it, probably what attracted me to astronomy and cosmology in the first place. So I'll talk today about, specifically about dark matter. But, I'll try to lead you through the various aspects that I tackle in the book. So in the book, dark matter is just one chapter. So each of these concepts is basically a chapter, and I talk about the origin of the idea, and I end with the current status of that big radical idea today. So as I mentioned, I'm interested in this process, and I'm interested in the use of maps as literal devices, and interested in the use of maps as mapping as knowing. If you're able to map something, that means you know something about it, even though your comprehension may not be complete. And this is, another hobby horse of mine. So when I was a kid, I was growing up in India, I was obsessed with maps. I would be sitting with atlases that I couldn't actually lift when I was a kid and be sort of looking through pages of them. And I was interested both in celestial maps and terrestrial maps. So, part of the interest in maps is sort of deeply rooted for me. And so I think one of the intriguing things about cosmology is that because the night sky belongs to all of us, right? So from time immemorial, the ancients have been looking up at the night sky and trying to make sense of it. And so the first known recorded description of the night sky is the Nebra sky disk. And this is a copper plate on which we see the Pleiades constellation, and we see the crescent moon and the sun, and it dates back to 2000 BC. So this is quite remarkable that we have this record. But what was intriguing, though, is sort of the gradual development of ways and means to chart and document the cosmos. So the Mesopotamians were great sort of inveterate recorders of the cosmos, and what you see there is the Venus Sky Tablet. It's from the Victoria and Albert Museum. This is a cuneiform tablet, and we've deciphered cuneiform, so we know what this is. This is a record of the positions of the planet Venus. Okay. And so you should kind of have sort of a sense of awe already that they actually knew the difference between a star and a planet already, right? And we're talking 7th century BC. But as we go on, there have been many sort of visualizations and attempts to understand the cosmos, to understand the order in the cosmos. But in particular, I think the ancients got a little hung up. Even up to the 1500s, people got hung up with trying to link the celestial to the terrestrial. They weren't really looking for what we would call a scientific explanation today. They saw these regularities, they saw these patterns, but they had not made the leap quite yet. Although the ancient Greeks had already sort of split mythos and logos, two different ways of a reasoned way, a questing way of looking at nature, and a mythical way, one with stories of dealing with nature. So that cleavage had happened, but it hadn't quite picked up as a way to organize epistemology and knowledge, right? But you have some very intriguing maps in the 1300s. So this is one of my favorites. And this is a map in which the angels are cranking at the corner, and they are the reason you have night and day. So, so notice we've suddenly moved from this sort of very static kind of descriptions of cosmos to sort of trying to understand why. What is the agency behind what's going on? And of course, the first radical idea that really set, in my opinion, everything that has followed, including the last 100 years in cosmology, was Copernicus. With Copernicus in 1543, he reordered the cosmos. So what he did, he just changed the pivot from the Earth to the sun. And remember, this was an extremely radical idea, and there was a lot of opposition from certain quarters. But the way it was dealt with was, and as happens a lot today too, when an idea is very radical, there's sort of a halfway house model that people find that acceptable, and then you eventually move from the halfway house to the full deal. So this is a depiction of Riccioli. It's actually the frontispiece of a book. And what you see is Urania, the muse of astronomy, weighing these two different cosmic worldviews. And I just want to remind you, for Copernicus, the universe was the solar system. They didn't know about anything beyond the solar system, right? And so you see these two models. So you see Copernicus's model, and you see the halfway house model that was Brahe's model. Basically, the Earth moved around the sun, but all the other planets move around the Earth. And so it's sort of this, kind of reluctance to give away pole position, Earth's pole position. But this is a very interesting graphic because you see sitting in the corner the very exhausted Ptolemy, and his Ptolemaic view of the universe has now been discarded. It has been superseded, right? So he's sitting in the bottom, kind of delegated to the bottom. And you might have noticed that also the telescope has appeared. So that's one-eyed Argus with the telescope, and you can see the telescope peeping out. So, the shift really in the 1600s happened from naked eye astronomy to using telescopes. And it was Galileo's repurposing the spyglass and turning it upward that kind of set this other radical stream going in terms of gathering evidence, data, making measurements, and actually recording them. But of course, the biggest, the next leap there came with photographic plates, where you could now record them and you had them available to revisit them. And you could have many people look at the data and make measurements and draw inferences rather than relying on one observer's notebook and their view through their eyepiece, right? So there were sort of a lot of dramatic changes in our conceptions of cosmos that happened after 1600. Obviously, there was Newton's theory of gravitation, the understanding of how gravity works, how the solar system is held in place. It's not collapsing into each other. I mean, all the planets are not running into each other. So there were dramatic changes that happened the 16, 17, 1800s. But fast forward to today. So this is where we are. We actually understand an incredible amount about the universe. And I think it still sort of stuns me, right, that with, a cantaloupe-sized gelatinous thing in our skull, we've been able to figure all of this out, right? And that is that the origin of the universe, we know the timeline. It's about 13.8 billion years since the start of time. And we start time from this moment called the Big Bang, which was not an explosion, incidentally. It just corresponds to a very hot, dense state of the universe. And the universe has been expanding, cooling since then. And we now know we can actually date the significant years, significant ages, stages in the universe's, in our universe's life history. So you first had the relic radiation, the cosmic microwave background, which we detect today as well. And then we know roughly when the first stars formed and when galaxies assembled. And we also know, interestingly, that this pie chart, the one on the left, is the composition of our universe. So we have a very peculiar universe. We happen to live in one in which the total energy content of the universe is dominated by two components that we don't know what they are. So 72% is dark energy, and dark energy is this mysterious force that was recently discovered, 1998. Two independent teams discovered that the expansion of our universe was actually accelerated. And in Ford, just like you need a gas pedal and you need gas to accelerate your car, dark energy is the universe's gas pedal. It's pushing galaxies much further apart from each other than normal expansion. And it's countervailing gravity in a way because it's a repulsive force that's pushing things apart. And that contributes today, so this is the inventory today. So this combination of constituents has morphed over time. As I mentioned, very early on, the majority of the budget was in radiation. And then eventually matter started to dominate. And then today, in the last 7 to 8 billion years, we think we live in a universe that's dominated by dark energy. And so notably, the matter content, the bulk of the matter in the universe, the stuff that experiences gravity, is dark matter. And we don't know what that particle is. And as I'm going, hopefully I'll convince you today that it exists. We have incontrovertible evidence from many independent lines of investigation for the existence of dark matter because of the effects it produces, although it has been not been directly detected yet. We don't know the particle. But I think the sobering thought is all the stuff that we're made of is 4%. That little science sliver that you see is us. So as I mentioned, I want to contrast, so in the book I contrast a lot of these ideas and I sort of compare in terms of their origin and who proposed them and what context these ideas came about. So I wanted to sort of bring these two into sharper focus because these are sort of areas that I work on. So they're both invisible entities, so you don't actually see a black hole, but you see material that's falling into a black hole that reveals its presence, right? And how they were discovered, as I said, were completely the opposite. The existence of dark matter was inferred from observational data, right? And black holes were sort of a mathematical, theoretical concept, and then eventually we found astrophysical objects that have those properties. So today I'll focus here on the evidence for dark matter. So there's two very, very important lines of evidence for dark matter. First is because it's gravitating and it is matter, even though it doesn't interact. So dark matter particles are peculiar. They don't actually reflect, absorb, or emit any light. They have mass, so they actually interact gravitationally. They cluster gravitationally, and and the model that we think that best describes the contents, the dark matter in our universe, consists of dark matter particles that are collisionless. They don't have pressure, which means that two dark matter particles are not going to collide like billiard balls. They're going to actually just graze past each other. And they would just get captured in their gravity. They could get bound, and eventually that's how they aggregate. And I'll show you some simulations of how dark matter actually aggregates. So we infer the existence of dark matter, and we not only infer it, as I'll show you, we can exquisitely map it at the moment, even though we can't see it because of the gravitational influence that it exerts. And then the other way in which we can detect dark matter is the impact that matter has on the propagation of light in our universe. And so the reason these two points are important is that the impact on the motions of particles, you could wear your Newtonian glasses, right? You could live in a universe where Einstein did not even happen, and you would infer that there was dark matter. And then if you wear your Einsteinian glasses and post general relativity, and general relativity predicts the bending of light, and you would then infer the existence of dark matter. And interestingly, there are objects called clusters of galaxies. These are the objects that I work on, which is about 1,000 galaxies that are held together, that are whizzing around and held together by the gravity of an enormous amount of dark matter. So clusters are the largest repositories of dark matter known in the universe. And it turns out you can apply both of these arguments to clusters and you infer the same amount of dark matter. So, I mean, in my opinion, that is, really, really strong evidence, compelling evidence, because they're completely different worldviews and they still converge and they give you, there's no escaping the concept of dark matter. Although people have tried to come up with alternatives. So the idea of dark matter was first proposed by this cantankerous Swiss astronomer who was at Caltech. His name is Fritz Zwicky. And he measured the speeds of galaxies. So what you see there is an old image of the Coma cluster, which I mentioned is about 1,000 of these galaxies that are kind of moving coherently. And you can measure the speeds. He measured the speeds and he found that they were whizzing around much faster than if the gravity was only contributed by all the stars and the gas that you see and the dust that you actually see in the picture. And in order to account for their speeds, you needed some unseen matter that was providing the gravitational pull for these galaxies. So that's what led him to postulate the existence of Dunkel materie, which is dark matter. And then in 1937, remember in 1915, 1916, Einstein came up with his theory of general relativity. And one of the key predictions of general relativity, as we'll see, is the bending of light because of the reconceptualization of the relationship between matter and space. And that's what Einstein did. And what that does is he conceived of the entire universe as space-time, this four-dimensional sheet in which mass. So he was actually able to explain what gravity is, not just how gravity works, because that's what Newton did. Newton told us how gravity works, and Einstein really taught us what gravity really is. And so he formulated gravity as the interaction between geometry and physics. So you have this fabric of space-time, and any matter in the universe would cause a divot or a pothole in space-time. And so space would tell matter how to move, as it were, and matter would, sort of codify how space should curve. So they have this sort of very deep, profound relationship. And therefore, space-time, there's nothing above space-time, there's nothing below space-time. That is the universe. So light rays travel in space-time. So light from distant objects will encounter many, many potholes due to the existence of matter as they whiz around to us. And light would get deflected or bent. It would no longer be straight paths. And, and I'm often reminded, this analogy of potholes came to me because I live in New Haven and our local highway is I-95. And I think it has the most potholes of anywhere else in the universe. And they're constantly constructing too, so I don't know what they're doing, right? They seem to be generating potholes. So, but it was useful because I realized that this is a very apt analogy. So light gets deflected, so you end up, as we'll see, distant objects are going to look distorted to us because of the bending of light. So Zwicky realized in 1937 that from the 1933 calculation, he realized there was a lot of unseen matter there. And then he realized there's so much unseen matter that there should be appreciable deflections in light deflections. But we still didn't have the instruments to detect that. In fact, it was not till the 1980s that we saw the first evidence for strong light deflection. So the kind of light deflection that Einstein predicted would happen, for example, during a solar eclipse, as I'll just show you, that was detected. And that's why Einstein became a celebrity very quickly, because in 1918, 1919, there was an expedition led by the English astronomer Arthur Eddington that sort of verified the prediction that Einstein had made. I'll just show you in a couple of slides what the actual prediction was. So in the 1970s, this is Vera Rubin and Ford, and Thonard. They started measuring, rather like Zwicky, but on a different scale, looking at the speeds of stars inside a galaxy as a function of the distance from the center. And they found something very peculiar, and they sat on this result for many years because it just looked crazy. And it's called a rotation curve, and what you see there shown in the white is that the speeds of stars as you go out from the center out seems to rise, kind of fall a little bit, and then stay flat. And this is, as you can see, in the outskirts of the galaxy when you've kind of run out of stars. So there has to be something that is matter that is holding up the outskirt of the galaxy, literally. There has to be dark matter, something there that is holding up and providing the gravity that is causing the stars at the large distances to move very rapidly. The reason why this is counterintuitive and why they sat on it for a while is to just look at the solar system. So if you look at the solar system and you plot the speeds of the planets around the sun, and in the solar system, the sun is the most massive gravitating body. So the speeds of the planets as you go further out is falling with distance from the sun. Okay, so here I should confess my blind spot. We all have our blind spots. Pluto is still a planet. I'm not able to give it up. I just can't give it up. So anyway, so as you go further out in the solar system, notice so this is the rotation curve of the solar system. The speeds are actually declining. So just to remind you, this is what's happening in a galaxy. So completely the opposite, right? So you have the speeds that are kind of increasing from the center out, reaching some kind of maximum, and then sort of tailing off and staying flat. And this was not the case for just one galaxy, but for many, many galaxies. So this is data from their 1978 paper in which they finally published it. And they said, okay, there is something quite different that's going on. And they proposed that there had to be unseen matter that was providing the gravity to support these motions. So this is our current cartoon understanding of what a galaxy is. So we think that the stars in a galaxy, which are concentrated in the center that we see, are just the tip of the iceberg in terms of the matter of the galaxy. Just 5 to 10% of the mass of the galaxy is what we see. Everything else is unseen. And it is spread, it's piled in the center, and it is piled in the outskirts. So we believe that all galaxies, including our own, have a dark matter halo around them. okay? And that the bulk of the matter, the mass of the galaxy, resides in the dark matter. So let's fast forward to this other independent way of trying to infer the presence of dark matter, and this is the discovery of light deflection. So the deflection of light was actually suspected even within the Newtonian framework, because there the idea was that light in Newton's time was believed to be made of particles, made of corpuscles, as he called them. So there were astronomers who calculated then that if you had a very massive object, you could actually gravitationally focus and deflect light particles, because you would attract them and you could change their path. And a Soldner in 1804 actually calculated what that deflection angle would be. And Einstein, as I said, completely reformulated gravity, right? I mean, it was completely reconceptualized gravity. And then in 1915, he also calculated that light deflection was one of the predictions of general relativity. And what is kind of curious is the classical calculation, in Newton's worldview, is just a factor of 2 off. With Einstein's prediction with general relativity. However, Einstein's prediction has been tested to a great degree of accuracy. So we know that general relativity is the right framework for what we know at the moment. So the light deflection, this is what Einstein predicted, and this is what really led to the very rapid acceptance of this radical theory of general relativity. And that was tested within a few years. And during a solar eclipse, you have the sun, earth, and moon line up. And if you can imagine, as I said, the sun creates a pothole, the moon creates a pothole, but a tinier pothole because it's a lot lighter than the sun. And therefore, if you have starlight from stars that lie beyond the sun there would get deflected. And you would end up seeing the stars to have an apparent position that was further away than they actually are. And how do you know that? When you don't have an eclipse, things don't line up. You don't have the pothole when things don't line up. And you can go back and look at the actual positions of the stars, say 6 months later or something. And that's what Eddington did. And what Einstein predicted was this displacement, this difference between the apparent star position and the real star position. And so that showed that general relativity was correct and predicted the right values. So this is our current understanding. This is a visualization of a cluster of galaxies. Remember I said it's 1,000 galaxies or so. And what is shown in the background is the pothole that is caused in space-time that you can see, and therefore light from a distant galaxy en route to us on Earth would get deflected, depending on which part of the pothole light traverses, right? So there are regions where light would get maximally deflected. In fact, there are regions, for example, where the divot is deep enough in the inner central regions here that if you imagine light rays to be like tubes, you actually end up splitting the tube. So you end up seeing multiple images of an object where in reality there's only one object. And the reason we know there are multiple images of the same object is, remember, all cosmic objects have a fingerprint, they have a spectrum. So we can go back and measure and we see that these multiply imaged objects, and I'll show you some examples, have the same spectrum. So we know that this description and this theory is correct and our interpretation is correct. So this is just another to just kind of impress upon you that there's a geometrical effect here. So the cluster of galaxies, the dark matter in the cluster of galaxies actually acts like a lens because it actually deflects, it focuses and defocuses light from distant objects. So do we see what does the real universe provide us? So this is an image from the Hubble Space Telescope where there's an individual galaxy has enough dark matter to cause severe light bending. So this is the image that you actually see on the sky, which is a highly distorted blue wisp, which almost a circle. And it turns out that we can analyze and we can figure out what's going on here. You have a galaxy that's shown in the central panel there that has a huge dark matter halo. And you have a distant galaxy that lies beyond it, and the light from that is getting bent out of shape into this arc, this very large arc. And you see this, you see many, many manifestations of this. This is all Hubble Space Telescope data on the right-hand side. And in the cartoon, showing you sort of what kind of dark matter distribution do you need to have in order to see those distortions, right? And so it turns out the universe, of course, is not simple. It's not your simplest blob, spherical blob of dark matter. It turns out that what we believe now is the best description for dark matter in clusters is a combination of all those clumps that you see there plus a smooth piece, both of them sort of simultaneously. So how do we know? So by the way, just a cautionary note, nothing in the universe is actually moving. This is just to show you a sequence of all possible stretches. Okay. So what you have is you have a uniform background in which all galaxies are basically little circles projected on the sky. And then in between that screen of distant galaxies and us, I've installed a massive cluster with a huge amount of dark matter that is causing all the deflection. And the cluster shows up, the mass of the cluster, the surface mass density of the cluster shows up as the shade of reds that you see. And you can see just right around the inner regions is maximal distortion. And it's all sort of very coherent. It's tangentially sheared, right? So it turns out that, with our conception of what galaxies should look like, so this is our conception of a galaxy on the left-hand side, a little bit of light, huge amounts of dark matter, and you see these very coherent distortions. You see these very coherent stretches that's actually seen in the data. In fact, we see everything, all the spectacular predictions we see. So here is a cluster of galaxies. It's a Hubble Space Telescope data. And you see 5 images of the same galaxy, 5 copies of the same galaxy. So there's only one galaxy in reality. And there is so much dark matter here. And the pothole is so deep that it's splitting light beams. And you're seeing 5 copies of it. So one of the other interesting things about gravitational lensing is that gravitational lensing actually magnifies the itsy-bitsy pieces that you are seeing, right? So the 5 copies, there'll be 4 of them that are magnified that I show in the yellow circles, and 1 of them will be demagnified, and that's a test for you to find, well, you can actually see it right in the center, right? So gravitational lensing is pretty amazing because it actually even brings into view faint galaxies that you would never, so they're nature's telescopes. And the power of this telescope, we will never, ever be able to build anything like this. And of course, the unfortunate situation with nature and in cosmology is that you can't do any controlled experiments. A cluster is where it is. I cannot move it and make it focus and move around, right? So we're stuck with that. But here's an example of another gravitational lensing cluster. And you can, by now, all of you should be able to pick out all the arcs, the distorted background objects that lie further. So the question is, okay, so what is this obsession with arcs? And what can we learn about dark matter by looking at this? So this is a simulation of the formation of a cluster of galaxies. So these are all dark matter particles. They're just mocked up to look like light and yellow because it's a color scheme that I liked, which is pink and yellow. So what you see are collisionless dark matter particles, which is cold dark matter particles, which we believe the current best guess for dark matter. And we see this cluster kind of assembling, and what I want you to pay attention to is the number of clumps, little clumps that you see. There's a lot of crud around, right? So you see sort of this smooth pink haze, and on top of it you see a lot of little clumps. And so it turns out that even though astrophysics may not help you pin down the dark matter particle, it can try to give you indirect clues to its nature. And one indirect clue that we have is from the amount of substructure, the amount of clumping that you see in dark matter. So if dark matter is this cold dark matter, you would see a lot of clumping. If it was a different kind of particle, right? So these are simulations where we have set forward with some initial conditions for the start of the universe. We are looking at the universe at the same time. And the only thing that's different is the nature of the dark matter particle. And notice how much smoother the universe is. So the goal that people like me have been following for the last few years is to use exquisite Hubble Space Telescope data. You need data from space in order to measure all the distortions accurately. Is to reconstruct the granularity of the mass distribution of these objects and try to compare to see which one it corresponds to. So, to let the cat out of the bag, it is cold dark matter, that all the data are currently consistent with cold dark matter. But let me just give you a quick idea of what I actually do and what we actually, those of us who work in lensing, what we actually do. So this is that same cluster that you just saw. And we're trying to reconstruct the dark matter distribution in this cluster, and you will notice there's a little yellow bunny rabbit region. That's the region behind which any source, any distant galaxy that you view through the bunny rabbit is going to get multiply imaged. So that's the deepest part of the pothole, if you will. So if you look down, if you think about this as looking down, so that's the deepest part of the pothole. And what you are seeing outside in the lines are, if you will, sort of the, you're sort of looking down at this divot. And so we're reconstructing, if you see the red kind of circles, the ellipses around galaxies in the cluster, those sort of give you a sense of the spatial extent of the dark matter that is associated with each of those galaxies. Remember, each galaxy has a dark matter halo that survives in the clusters. So this is the kind of map that we're making now. So this is a distribution of dark matter in this cluster. So you see a smooth component that is kind of heaped, and then on top of it you see a lot of spikes which are clumps, okay? And so our current reconstruction, the best to date, so this is sort of hot off the press, the deepest ever data taken of a cluster of galaxies is part of this project undertaken by the Hubble Space Telescope, and that is called the Hubble Frontier Fields. So this is a galaxy cluster at very early times, which is in the process of assembly. There's a huge amount of dark matter in it. On the left-hand side, this is what we see. On the right-hand side is a reconstruction and overlay of the dark matter map on top of it. So the blue haze is the stuff that we don't see, which is there because of the light bending. Okay? This is what we infer. And so once again, this is a visualization, and you can immediately see that it's very clumpy. The dark matter is extremely clumpy, and it looks much more like the cold dark matter that I told you. However, before we get carried away too much, when we try, all attempts to detect and discover the particle have given us null results at the moment. Nothing. And there are different ways in which people have been trying to look for them. And so one experiment so there's one controversial result, because, I'm talking about radical ideas, so it behooves me to talk about controversial results. So there's a result that was a claim by an Italian collaboration about 15 years ago of detection of the kind of seasonal modulation that you expect because of our motion, with the dark matter background in which we are embedded in, right? So our galaxy has this dark matter, and the solar system has some dark matter, not a whole lot of it, but, we would expect a seasonal variation, and they claim that detection. And that's controversial, and in essence, what that experiment did is they took a crystal. In this case, it was sodium iodide, and if you can imagine a crystal to be sort of atoms with springs connected, so basically you have a dark matter particle, this sort of lazy, cold dark matter particle going through, jiggling the crystal slightly, and that's sort of what you're trying to measure, right? And so obviously the uncertainties are the rate, how frequently these particles, they're actually quite lazy, not that many going through. And as I said, because they don't interact, right, they do really nothing. I mean, dark matter particles have gone through us doing nothing. They've not rearranged the atoms in our bodies, right? They just go through. That's how boring and inert they are. They do nothing, right? But luckily for science, finally, right, one of the interesting things about science is replicability. And the fact that, the same company that made the same sodium iodide crystals has now made 5 different copies. And this experiment is now being repeated in 5 locations in the world, including Antarctica, South Korea, Germany, and Spain, as well as Italy. And so we'll see in 3 years, the combined data from all these experiments, we'll be able to evaluate the original claim and see whether it stands or it falls. So you may say, what is it that people like me are after, right? And I think this is my final slide. And what we really are trying to do, we know that Einstein's theory of general relativity is not the final word, because and that it's an incomplete theory, because we don't have a quantum theory of gravity. We don't have a quantum mechanical understanding of gravity yet. String theorists have been at the job. Einstein himself worked on it for the rest of his life with no success. And there have been some advancements, but we just still don't have a theory. That's where we are. So, and so what people like me are doing, and for me personally, the motivation is to look for gaps, look for disagreements, and look for anomalies where an observation is actually inconsistent with a theoretical expectation, right? And so there, history has some very interesting lessons to teach us. And the first one is that in the 1700s, the orbit of Uranus, as predicted by Newton's laws, seemed to have an anomaly. It didn't actually, and Newton's laws were sacred. So, it was a bit of a kerfuffle. Oh, what's really going on here? Newton could not have been wrong. So it turns out that a French mathematician, Urbain Le Verrier, came up and said, well, I know what's going on. What's going on is there's another gravitating body beyond Uranus whose gravity needs to be taken into account, that will perturb the orbit of Uranus slightly, and that's what's happening. So he predicted the existence of Neptune. People looked, and they found it, right? He was able to pinpoint and say, and Newton's laws remained intact. So there's just a refinement of the theory and a refinement of our understanding of the solar system that happened, right? Similarly, there was a problem with the orbit of Mercury. There was a precession in the orbit of Mercury that was not explained by Newton's laws. And this was, again, Urbain Le Verrier said, oh, same idea. Basically, what's happening now is that you have another planet, and this planet was called Vulcan, between the Earth and Mercury. And people tried to go look for it, and some people claim to find it, but actually there is no Vulcan, right? And in order to explain the anomaly, an anomalous precession of the orbit of Mercury, you needed a radical re-understanding. You needed Einstein's theory of general relativity. You needed the divot. You needed that pothole. And Mercury samples the closest to the pothole that's generated by the sun, right? And so in one case, the theory remained intact, and it just refined an anomaly, refined our understanding. In the other case, it pointed the way to the existence of a more fundamental covering theory that was yet to come. It took 74 years, after which Einstein actually came up with his theory of general relativity. And it was not, he wasn't motivated. Einstein was not setting out to explain this anomaly, right? It turns out that his theory, Einstein is very famously known for, in a way, we all admire him so much because general relativity came out of pure thought. And all he did was thought experiments, Gedanken experiments. Although he knew there were real experiments, and he knew that. He knew Newton's laws, and he knew about Galileo's experiments from the Tower of Pisa. But, it turns out that what really needed to happen was a fundamental remaking of the theory. So one is looking for gaps because you never know whether you are in a Uranus situation or you're in a Mercury situation. And we already know that, the theory is incomplete, so we absolutely are, excited to find. And my attempts with all this lensing work, right, has been, I was really fondly hoping, when I finished graduate school, so my first project was my first idea was to really map dark matter and the granularity of dark matter. And I thought, this is great. I'm going to become really famous because I'm going to find a problem in cold dark matter, right, that it doesn't work. Frustratingly, it works really well. Still, and I'm still waiting for that anomaly. So anyway, thank you so much for your attention, and I'd be delighted to answer questions.
Hi, everybody. So please line up on either side and come up to the microphone with any questions. Please keep your questions short, to the point, and in the form of a question, all right? Thank you.
Thank you. Do you have any information or thoughts about the existence of white holes?
Yeah, they're mathematical entities, so they're permitted, but they're not real. Crisp, yes.
So you explained the lensing and so on. But it seems like I can sort of see why it would curve it back around, but why wouldn't it just kind of deflect this light off into nowhere?
There
one
would be
question.
some light rays that would be deflected off
Okay.
and would go nowhere. But remember, the idea is that the sources that are producing the light are spherically, symmetrically producing light
Okay.
in all directions. And the stuff that's coming towards us is the stuff
Just
that's going to
goes
get deflected.
around.
And the stuff that's scattering away and going other places
Yeah.
would continue.
Okay, and the other thing is the dark matter, apparently it's transparent because it's going through these galaxies and so on,
Yep.
and it's still
It
got
doesn't
mass.
interact with light at all. Yeah. Or with any atoms.
Any atoms.
Yeah. Nothing on the periodic table. It doesn't interact with anything, as far as we know. Yeah. It is the most peculiar thing.
Yes.
But it aggregates in the right way to explain everything that we see, because it experiences only gravity. Right? Oh, yeah.
One of your slides that was my favorite showed two pie charts. One is the distribution of matter and energy today, and the other was at an early stage of the universe. And I assume then we're figuring out how it must have been in the early stage of the universe by what it looks like when we're looking at very distant objects that, because we're seeing essentially back in time. So we're able to determine that there are four phases you're talking about: energy, dark, energy, light, matter, dark, matter, light. All four of those phases reveal themselves by observations of distant objects?
Yeah.
Wow.
Yeah. It's pretty incredible. Yeah. And in fact, we can even pinpoint where things are morphing when you are moving from radiation dominated to matter dominated to dark energy dominated. We can actually pinpoint the times. Yeah, and I think one of the most sort of intriguing, abstract, and sort of mind-blowing concepts for me too still is the fact that when you look out into the universe, you are looking back in time. That is just incredible, right? I mean, the fact that you are seeing light. So, for example, it takes light 8 minutes to reach us from the sun. So if the sun shuts off, we won't know for 8 minutes. So the sun is our nearest star. It's not going to shut off for several billion years. But the sun is our nearest star. And so you can imagine just extrapolating, right? So these distant galaxies, which are much, much further away from us, light has taken billions of years to actually reach us. And so when we look out into the universe, we are seeing the universe as it was, not as it is, because that galaxy that you are seeing today, what it's doing at this moment, we don't actually know. It could have, all the stars could have died. It could have, it could not actually been there. It could have merged with something else. So I find that still quite mind-blowing, I have to say.
So the formation of black holes from the collapse of supermassive stars, you mentioned another mechanism that. Can you describe that mechanism?
Absolutely. So this is like, you've got to stop me now because this is my pet, right? So I'll keep going. I'll try to keep it brief. So these are what are called direct collapse black holes. And the idea is that very early in the universe, before the formation of galaxies in pre-galactic stages, what you had these dark matter potential wells. You had these dark matter aggregates, these regions, which pulled in gas because of the gravity. The gas came in, and the gas was sort of swirling around. And when gas has a lot of spin or rotation, it tends to settle down as a disk. And so you've had these sort of pre-galactic disks, which are basically hydrogen, mostly hydrogen. And there are instabilities you could have in this disk that would drive the gas down right into the center at very, very rapid speeds, rather like when you take out the plug from your bathtub and you see the water really going down really fast. You have a certain kind of instability in these gas disks that actually prevents the gas from fragmenting. If it fragments, you form stars. So you want to prevent that. So it's a particular kind of global instability. The whole disk is unstable, and the stuff gets swirled and sent in, and you very rapidly condense a lot of matter into a very tiny space in the center. And that's how you form these direct collapse black holes. And we think that there are conditions available in the early universe for this to happen, for this kind of process, the collapse to happen. And the cute thing is that these black holes would be about 10,000 to 1 million times, up to 1 million times the mass of the sun from the get-go, Whereas the end states of stars, you start out kind of piddly, 10 times the mass of the sun, maybe, 20 times the mass of the sun. And so we are now seeing, as I mentioned, that the way black holes reveal themselves is by the gas that is flowing into them, that's being captured by them, that gets heated. And so the gas is heated to such high temperatures, like 1,000,000 degree Kelvin, that it starts glowing in the X-rays and in optical light. This is just a gas, the dying gasps of gas as it's sort of falling in. And so we see these objects, they're called quasars, and we see them back in time. Very, very early on, you see these extremely bright quasars, which are outshining the galaxy that they're sitting in. So they're that bright, which means they're powered by a supermassive, if not ultramassive black hole, which was already in place when the universe was a fraction of its current age. So it's kind of a timing problem and kind of a feeding problem. If you start with something that is really piddly, like 10 times the mass of the sun, growing a black hole from there to 1,000,000,000 times the mass of the sun within a few billion years or few 100 million years is challenging in the universe. Whereas if you, from the get-go, can make a monster black hole, then the feeding problem is alleviated. So that was the motivation for suggesting that you could have these direct collapse black holes. Anyway, the idea stands to be tested by the James Webb Space Telescope. And it's a very peculiar thing that can be tested. So it turns out that the properties, the mass of the black hole in the center of the galaxy is correlated to the mass of the stars in the innermost region. So if you look at all the galaxies near and around us, where the black holes are basically dead. So the black hole in our galaxy is dead, it's no longer feeding, it's never gonna, in the past it might have lit up as a quasar, but no more. There's not enough gas, it's not feeding. But if you draw a plot, in the mass of the black hole is roughly 4% of the mass of the stars in the inner region of the galaxy. And that seems to be, that holds for most galaxies, about 4% roughly for all of them. And the question is, what causes, why do you have this correlation? When does that happen? So it turns out that if you make a very, very massive direct collapse black hole, there is a brief period of time when the black hole is more massive than the stars that are going to form in that galaxy before it flips and it becomes 4%. And that is detectable by the James Webb Space Telescope, a period when the black hole will outshine all the stars in the galaxy. It's a very brief period in the very early universe, and that's what you would be looking for. So it's a very clear signature. In fact, we just actually put out the paper predicting what the spectrum should look like, and it should be booming. If they're there, James Webb should see them.
What's our best shot at getting any information older than the cosmic background?
You mean directly?
Yes.
Okay, so indirectly we do because we have since we know the thermal history of the universe quite exquisitely, right? So for example, we know that all the hydrogen and the helium in the universe up to lithium formed in the first 3 minutes of the universe. So we have measurements of what fraction of the universe is hydrogen, mostly hydrogen. Universe is mostly hydrogen and helium, right? And so we actually have that pinned down. So we've gotten to indirectly to 3 minutes, if you will. So I think a few years ago there was a claim of a detection of gravitational waves from inflation in the very early universe by this collaboration called BICEP. That result went away because the effect is mimicked by dust nearby our galaxy. And they had not accounted for the distribution of dust appropriately. And so that signal, the effect that dust would produce, it's a kind of a swirly pattern in the cosmic microwave background. That is a signature you would get from gravitational waves from the very, very early universe, much like the LIGO event, except this is from the universe itself. So it's sort of a hum that you would have of gravitational waves in the background. And so I think the detection of gravitational waves by BICEP, these instruments, that would be the farthest that we could actually go. That would be 10 to the minus 43 seconds after the Big Bang. I'd be thrilled with that. Sorry?
Has that study been replicated?
No, there are many groups. Yeah, absolutely. Many different groups have been funded, and even BICEP has been funded. And, and there are going to be independent analysis. And I think there'll be enough data, probably enough signal in, it's a really challenging measurement. And the analysis is really challenging. And, the measurements were made in Antarctica. So I think, again, another 3 to 5 years, we should, if it's there, we should, if they're really there, we should know. And if we detect them, that stands to ratify this picture of inflation. But inflation is required to explain our universe, no matter what. I mean, the sort of the uniformness of the cosmic microwave background, the fact that the differences in temperature that we see in the relic universe are at the level in the 5th decimal place, right? So that uniformity you cannot have unless you had this very early sort of exponential expansion phase for the universe. So, I think that would be quite the exciting, I'm looking forward to that. So, I mean, I'm looking forward to that, but the thing that I'm really looking forward to is the merger of 2 supermassive black holes. So, LIGO saw the merger of 2 30 solar mass black holes. So, the stuff that I work on are much more massive black holes. A supermassive black hole is just a fancy way of saying something that's 1,000,000 times the mass of the sun. And so these will be constantly merging in the early universe because galaxies merge and they grow by merging. And the gravitational waves that you get out of that merger are much lower frequency than LIGO. And you cannot detect them from Earth. So you actually need a LIGO-like instrument in space. And that's being planned, and it's called LISA. And I think the Europeans have been pushing for it, and there's a prototype was sent out. It performed better than spec. So, technology is not a limitation, it's just money. So I think the US is reluctantly and grudgingly joining in because after the LIGO discovery, right, it would be an utter shame to not be in the game.
2 quick questions. You used the word seasonal for...
Sorry, I used the word, sorry?
Seasonal?
Yeah.
For the detection the Italian team was doing.
Seasonal variation, a modulation because of the seasons.
Okay, I'm a little confused. How does that affect the season's effect?
It's not the seasonal effect is because of the relative position of the Earth and the Sun. So if you can think of dark matter as a wind, so we have,
Gotcha. Okay.
there's a modulation.
And then the other question is, dark matter is clumping and clustering gravitationally. Is it part of black holes? Any black holes?
It could be. Once anything passes the event horizon of a black hole, it doesn't matter. I mean, you never know where it came from. So you could have black holes that were fed by dark matter. So it just turns out that the density of dark matter in the inner parts of galaxies, which is where the supermassive black holes tend to reside, is actually quite low, and gas is much more densely and more copiously available. So we think that most of the black holes, so for example, if you try to dissect the black hole in the center of the Milky Way, much less than 1% of the mass of the black hole is 4 million times the mass of the sun. So much less than 1% of that could have come from dark matter. But that's a great question. And in fact, the converse has now been suggested. So there's actually a scientific paper that has suggested after the LIGO detection that maybe all of dark matter is 30 solar mass black holes. Can we make it? And it's a cute idea, but it's not clear that it's going to stand tests.
We have time for just one more question.
All right, I got lucky. Mostly, I was just curious if you could share any resources or blogs or articles or things that were impactful to you in your journey of learning more about the universe, or things that you would recommend for folks who are kind of newly interested in learning more about the cosmos.
Oh, cool. So first of all, okay. I'm in my 40s, so there were no blogs. Okay, you didn't hear that? You don't know how old I am? Okay. So, no, but I think there's a lot of wonderful information now online, right? So, for example, there are websites by institutions like the Space Telescope Science Institute has amazing websites. NASA has great websites. And I tend to, also, Scientific American does a wonderful job, and they have blogs online as well as the actual print magazine that still comes out. So I think, there's actually there's no dearth of resources. In fact, there's a problem of sort of fire hosing. There's too much information, and how to organize. So in terms of what I personally read and devour, I look at all the NASA websites, all the sort of the Space Telescope, NASA, and I also look at space.com. And there's some places where the aggregation, I think, is just like fabulous. So I think there are lots of online resources, but I actually do, not just because I've written a book, but I do like real books. I like actual books. And I think also there's a rash amongst us. Someone told me that this is a rash amongst us astrophysicists to start writing books for the curious public. So there's plenty of books. There's some excellent books out there as well. And I do like the remake of Cosmos by Neil deGrasse Tyson. I grew up on Carl Sagan, but I do like this one. In particular, I like the way in which the animation is kind of mixed in very, very nicely. So hope that was helpful. Thank you very much.